A neutron star is already one of the universe's most extreme survivors, but sometimes, after a massive star dies, or after two dead stars collide, something even rarer may appear: a magnetar, a compact remnant whose magnetic field can overpower nearly everything around it. It may flare, fade, twist its own crust, or vanish into a black hole before astronomers can ever see it directly. And sometimes, the most important clue is not a signal at all, but the silence left in the radio sky years later. Welcome to Boring Science Stories. If this kind of calm cosmic mystery helps you relax, please like the video, subscribe to the channel, and share it with someone who enjoys quiet science before sleep. Thank you for spending your time here. Where are you watching from, and what time is it for you right now? Leave a comment below. Now, let's begin the short, violent life of a magnetar. A magnetar begins with a star that has already used almost everything it once had. For most of its life, the star is held in balance by fusion, the process that joins lighter atoms into heavier ones and releases energy from the core. That energy pushes outward, while gravity pulls inward, and for millions of years the two pressures hold each other in a difficult truce. But a massive star cannot keep that balance forever. Its fuel changes, its core grows heavier. The reactions that once supported it become less efficient, and the center begins to approach a limit where no ordinary pressure can hold it up. When that limit is reached, the collapse is not gentle. The outer layers may still look like a star, but deep inside, the central region falls inward with astonishing speed. Matter is squeezed beyond the conditions found in ordinary atoms. Electrons and protons are forced together, forming neutrons, while the core becomes so dense that a small remnant can contain more mass than the sun packed into a sphere only about the size of a city. This is the birth of a neutron star, one of the most compact, stable objects known in the universe. It is not a normal star anymore. It is the exposed core of something that has died violently, left behind after the outer layers are driven away in a supernova. Most neutron stars are already extreme enough without needing any further label. Their gravity is intense, their surfaces are dense beyond everyday comparison, and many are born spinning rapidly, carrying magnetic fields inherited and compressed from the star that created them. When their magnetic beams sweep across space and happen to cross Earth, they can appear as pulsars, repeating radio sources with remarkable regularity. A pulsar is not flashing because it turns on and off like a lamp. It is rotating, and its emission is directed in beams. Each time one of those beams crosses the line of sight, a pulse is recorded. In this sense, many neutron stars announce themselves through rhythm. They are compact clocks made from collapsed stellar matter. A magnetar belongs to the same family, but it occupies a rarer and more severe branch of it. Its defining feature is not simply fast rotation, although some may be born spinning quickly. Its defining feature is its magnetic field, which is far stronger than that of an ordinary neutron star and powerful enough to dominate the remnant's behavior. The field is not a decoration around the object. It is an energy reservoir, a source of stress, and in many cases the reason the magnetar is visible at all. A neutron star can be understood as matter pushed to a boundary. A magnetar is that same boundary, but threaded with magnetic forces so intense that the crust itself can be strained by them. The difficulty begins with the origin of the field. All stars can have magnetic fields, but a magnetar requires something far beyond the usual inheritance from a stellar core. During collapse, magnetic field lines can be compressed along with the matter, making the field stronger simply because it is squeezed into a much smaller volume. That alone may not be enough. The newborn neutron star may also rotate rapidly, and if its interior is convective and turbulent in the first moments after formation, motion inside the star could amplify the field through a dynamo process. a mechanism in which moving electrically conducting material strengthens and organizes magnetism. This idea is one of the main ways researchers explain how a magnetar might be born from a single collapsing massive star. But the formation is not yet a settled story. The universe does not provide a clean laboratory where the same star can be collapsed repeatedly under different conditions. Each event is brief, distant, and partly hidden inside expanding debris. The supernova may reveal that a massive star has died, but the newborn remnant at the centre can be difficult to see directly. The outer layers of the star race outward. Dust and gas scatter and absorb radiation. The young neutron star may be surrounded by material still reacting to the explosion. Even when a magnetar is later identified in the Milky Way, the moment of birth is usually long past. This is part of what makes magnetars scientifically important. They are not only strange objects in their own right, they are clues to the hidden physics of stellar death. A massive star does not become a magnetar merely by being massive. Many massive stars collapse into neutron stars without producing magnetars, and some collapse into black holes instead. Somewhere in the details of mass, rotation, magnetic inheritance, internal motion, and explosion geometry, a small set of conditions appears to push the remnant into magnetar territory. The result is an object that may contain more magnetic energy than rotational energy, meaning its visible behavior can be powered less by spin and more by the slow rearrangement and decay of its field. This distinction matters because it separates magnetars from ordinary pulsars in both behavior and lifetime. A pulsar gradually loses rotational energy as it emits radiation and particles. Its spin slows over time, and its pulses can remain detectable for long periods if the beam continues to cross Earth. A magnetar, by contrast, can be more erratic. It may produce bursts of high-energy radiation. It may brighten suddenly. It may change its pulse pattern. It may release energy when magnetic stress fractures or shifts the crust, or when the external magnetic field rearranges itself. The object is small, but its activity reflects an interior and exterior under continuous strain. Yet even here, the language of violence must be kept precise. A magnetar is not continuously exploding. It is not a star burning in the ordinary sense. It is a compact remnant with stored magnetic energy, and that energy can emerge unevenly through flares, outbursts, and persistent X-ray emission. Its life is short not because it vanishes immediately, but because the period during which it behaves as an active magnetar may be brief on astronomical timescales. The strongest magnetic fields decay or reorganize. The remnant cools. Its bursts become less frequent. What begins as an extreme newborn object can fade into a quieter neutron star whose earlier intensity is no longer obvious. That fading makes the birth problem harder. If magnetars are most recognizable when young, then many older examples may be hidden among the broader neutron star population, their magnetic history partly erased by time. The known magnetars are therefore not just isolated curiosities. They are the visible survivors of a larger process that may be difficult to count. Some appear within or near supernova remnants, suggesting a connection to massive star collapse. Others are identified by their high-energy behavior rather than by a clearly preserved birthplace. The evidence points strongly to neutron star origins, but the exact pathway from collapsing stellar core to magnetically dominated remnant remains open. The short, violent life of a magnetar begins. Then, not with mystery alone, but with an established sequence of physical events. A massive star exhausts its core. Gravity wins the central contest. Matter collapses into neutron-rich density. The outer star is expelled. A compact remnant remains. From this known foundation, The rarer question begins: why does this remnant become a magnetar instead of an ordinary neutron star? The answer must lie in the first seconds after collapse, when the newborn object is hot, unstable, rapidly changing, and still connected to the explosion around it. Those early moments determine whether the magnetic field remains strong enough to shape the rest of the remnant's life. They may also determine whether the object will later reveal itself through bursts, X-rays, or other signs of magnetic stress. In that sense, a magnetar is not only the corpse of a massive star, it is a record of the collapse conditions that made it. Its surface, field, rotation, and fading activity all point backward to an event that can no longer be replayed. What remains is the remnant itself, carrying the evidence of an extreme beginning in a field strong enough to make an ordinary neutron star seem almost quiet by comparison. A magnetar is defined less by what it is made of than by how its magnetic field controls the matter around it. The object itself is a neutron star, with a crust of dense material above an interior, where particles are packed into conditions that cannot be reproduced on Earth. But in an ordinary neutron star, the magnetic field is often one important feature among several. In a magnetar, it becomes the dominant source of visible activity. The star may still rotate, cool, and emit radiation. Yet the field supplies the tension that makes the object unusual. It shapes the outer layers, fills the surrounding space with charged particles, and stores enough energy to produce bursts long after the original supernova has faded. The field is not simply strong in the everyday sense. It is so intense that the usual separation between matter, radiation, and magnetism begins to feel less useful. Electrons moving near the surface do not behave as they would in a laboratory magnetic field. Radiation passing through the magnetosphere, the region controlled by the star's magnetism, can be scattered, redirected, and reshaped by that environment. The surface is not just a surface. It is the inner boundary of a magnetically stressed system. The first source of this intensity is compression. A massive star already carries magnetic structure before it dies. When its core collapses into a neutron star, the same broad magnetic pattern is forced into a much smaller volume. If the field lines remain tied to the conducting matter, the shrinking of the core strengthens the field dramatically. A loose comparison can be made without exaggerating the simplicity of the process. When the same magnetic flux is confined to a smaller area, the field becomes stronger. Stellar collapse carries this idea to an extreme. A core that once occupied a region many thousands of kilometers across is reduced to a remnant only about 20 kilometers wide. The change in size alone can turn an ordinary stellar magnetic field into something far more powerful. But magnetars appear to need more than compression. Many neutron stars are born from collapse, and only a small fraction become magnetars. Something in the earliest moments must amplify or preserve the field beyond the usual outcome. One leading possibility is a dynamo inside the newborn neutron star. In this context, a dynamo is a process in which moving, electrically conducting material builds magnetic field from motion. The newborn remnant is hot and unstable. Its interior may churn, its rotation may be rapid. If those conditions are strong enough at the same time, magnetic fields can be wound, stretched, and reinforced before the star settles into a more rigid state. The key requirement is speed. The process must act while the neutron star is young enough for its interior to move freely, and while rotation is still fast enough to provide energy. If the remnant is born spinning slowly, or if internal motion becomes quiet too soon, the magnetic field may never reach magnetar strength. This gives the formation problem a narrow shape. A magnetar may not be produced simply by collapse, but by collapse under conditions that briefly allow motion, heat, and rotation to cooperate. Once the field exists, it changes the way the neutron star lives. The solid crust of a neutron star is not thick in ordinary terms, but it is immensely strong. It is made of compressed nuclei and electrons arranged under gravity far beyond the strength of any planet. Even so, the magnetic field can stress it. The field threads through the interior and extends outward into the magnetosphere. If the internal field shifts as it slowly evolves, the crust may be pulled out of equilibrium. It can bend, crack, or rearrange, and that sudden change can release energy into the outer magnetic field. This is one explanation for magnetar bursts. The burst is not powered by chemical burning or ordinary fusion. Fusion has ended. The energy comes from magnetic stress, stored in and around the neutron star, then released when the structure can no longer remain in its previous state. This makes a magnetar different from a normal pulsar in a practical observational sense. A pulsar is usually powered by rotation. It loses rotational energy gradually, and that loss can drive beams of radiation and particles. Its timing can be steady enough to measure tiny changes in spin over many years. A magnetar can also rotate and can sometimes show pulses, but its strongest behavior is often tied to magnetic energy instead. It may brighten suddenly in high-energy radiation. It may produce short bursts lasting fractions of a second. On rare occasions, it may release giant flares that briefly outshine much of its usual output. These events do not require the star to be young in human terms, but they do require that enough magnetic stress remains available. The field is therefore both the source of the magnetar's power and the reason its active life cannot last indefinitely. The magnetic field also controls the surrounding plasma, the thin gas of charged particles near the star. Close to a magnetar, particles do not drift freely as they might in weak fields. They're guided along magnetic structures, accelerated by electric currents, and involved in radiation processes that can make the object visible across great distances. The magnetosphere can become twisted if the crust shifts the footpoints of magnetic field lines anchored at the surface. A twist can increase currents in the magnetosphere, and those currents can heat the surface or scatter radiation coming from below. The result may be persistent X-ray emission, changing pulse profiles, and outbursts that fade over months or years. None of this requires the magnetar to be large. Its influence comes from how much energy is packed into its field and how efficiently that energy is transferred into particles and radiation. The interior field may be even stronger than the external field that can be estimated from spin measurements. Observers often infer a magnetar's surface field by measuring how its rotation slows with time. A stronger dipole field, the large-scale magnetic field shaped roughly like that of a bar magnet, should remove rotational energy more efficiently. But the external dipole is only part of the story. Hidden magnetic structures inside the crust or core may carry major amounts of energy without appearing directly as a simple dipole. These internal fields can still stress the crust and drive activity. This distinction helps explain why some magnetars may not look extreme by one measurement alone. The magnetic engine may be partly buried, and its effects appear through outbursts rather than through a single number assigned to the surface field. Over time, that engine weakens. Magnetic fields in neutron stars do not disappear quickly, but magnetar strength fields can evolve and decay on timescales much shorter than the full life of the remnant. Currents dissipate, heat escapes, the crust relaxes into new arrangements, the star cools, and the available magnetic energy becomes harder to release. The magnetar may still remain a neutron star for an enormous span of time, but its identity as an active magnetar is tied to the period when the field is strong enough and unstable enough to produce recognizable behavior. This is why magnetars are often described as short-lived in an astronomical sense. Their visible activity may be concentrated in the first few 1,000 to 100,000 years after birth, while ordinary neutron stars can remain detectable as radio pulsars for much longer. That short active lifetime affects how magnetars are counted. The known population may represent only those objects that are close enough, young enough, or active enough to be noticed. Some older magnetars may have faded until they resemble less dramatic neutron stars. Some may be hidden by distance, dust, or unfavourable viewing geometry. Others may be born in environments where their early signals are absorbed or confused with other emission from the supernova remnant. The field as an engine therefore creates both the object and the observational challenge. It makes magnetars bright and erratic while the energy is available, then allows them to quiet down as the field evolves. The same mechanism that reveals them also places a time limit on how long they remain easy to recognize. The central idea is simple, but its consequences are deep. A magnetar is not powered primarily by ongoing nuclear reactions, because those ended with the death of the massive star. It is not defined only by rotation, because rotation alone describes many pulses. It is a neutron star whose magnetic field has become the main reservoir of usable energy. That field stores stress, transfers energy into the crust and magnetosphere, and produces the bursts and high-energy emission that make magnetars stand apart. The violence of the object is therefore not constant motion or continuous explosion. It is stored energy under pressure, released unevenly as the field changes. The next problem is why only a few neutron stars enter this state. If collapse can make a neutron star, and compression can strengthen a field, then the rarity of magnetars means that another filter must be operating. The field is the engine, but the deeper question is why the engine starts in so few remnants at all. The rarity of magnetars is not obvious from the first step of their formation. Every neutron star is born from an extreme event, and every neutron star begins with compressed matter, rapid change, and a magnetic field made stronger by collapse. At that level, the ingredients seem common enough. Massive stars die across the universe. Supernovae leave compact remnants. Pulsars are found in large numbers, each one carrying the imprint of a collapsed stellar core. Yet magnetars form only a small part of the known neutron star population, and that imbalance is the first sign that collapse alone cannot be the whole explanation. Something must separate the few remnants that become magnetically dominated from the many that become ordinary pulsars or quiet neutron stars. The difference may be decided almost immediately after birth, during a short interval when the new object is still hot, fluid, and unstable. Later, when the crust has formed and the star has settled, the chance to build an extreme magnetic field may already be gone. This makes magnetar formation a problem of timing as much as power. The right physical conditions have to overlap before the remnant becomes too rigid to change. One of the most important conditions is rotation. A newborn neutron star can spin very quickly because the collapsing core preserves angular momentum, the tendency of rotating matter to keep rotating as it shrinks. As the core contracts, even a modest initial spin can become much faster, in the same broad physical sense that a shrinking rotating object turns more rapidly when its mass is pulled closer to its axis. But not every collapsing core arrives with the same rotation. Some massive stars lose angular momentum before death through stellar winds, internal mixing, or interaction with a companion star. Others may keep more of it. If a magnetar requires an especially rapid spin at birth, then only the remnants of certain stars will qualify. This helps explain why magnetars are rare without making them mysterious in a vague way. Their rarity may reflect a narrow starting condition. The neutron star must not only form, it must form with enough rotation to feed a strong dynamo before the early turbulence fades. Rotation by itself still may not be enough. The interior of the newborn neutron star must also move in the right way. In the first seconds after collapse, the remnant is hot and rich with neutrinos, nearly weightless particles that carry energy out of the core. The star is trying to cool while also settling into a stable structure. Layers may overturn, material may circulate. If those motions are strong and the rotation is fast, the magnetic field can be amplified. If the motions are weaker, poorly organized, or too brief, the field may never reach magnetar strength. The outcome depends on a complicated early state that cannot be observed directly. The supernova shows the large-scale result, but the field is shaped inside a tiny remnant hidden at the center of the blast. This is why magnetars are difficult to connect cleanly to their birth conditions. The most important part of the process happens behind the explosion, deep inside matter that cannot be seen as it changes. The mass of the remnant adds another filter. A neutron star survives only within a limited range. If the collapse core is too light, it may not form a neutron star in the expected way. If it is too heavy, it may continue collapsing into a black hole. Between those outcomes lies a narrow region where a neutron star can remain stable. Magnetar formation may require the remnant to sit in an even more particular part of that region massive enough to be energetic and compact, but not so massive that it disappears into a black hole before its field-driven life can begin. This matters because massive stars do not produce identical cores. Their final structures depend on initial mass, metal content, mass loss, rotation, and whether they have companions. The collapse may also be asymmetric, with some material expelled and some falling back onto the remnant. Fallback can change the spin and may bury or alter magnetic fields. Instead of a single clean path, there may be many nearby outcomes, most of which do not produce a recognizable magnetar. A star may form a normal pulsar. It may form a weakly magnetized neutron star. It may form a magnetar whose activity is hidden by debris. It may form a black hole. The rarity of magnetars may come from how few collapsing cores pass through the required corridor without being diverted. The explosion itself also matters. A supernova is not just a shell leaving the star. It is the environment into which the new neutron star is born. The outward-moving material can obscure signals from the remnant, and the behavior of that material may record how much energy the central object has injected. Some unusually bright supernovae have been interpreted as possible signs of a newborn magnetar adding energy to the expanding debris. In that picture, the magnetar acts as a central engine, spinning down and transferring energy outward, making the supernova brighter or longer-lived than it would have been from the original explosion alone. But this does not mean every superluminous explosion contains a magnetar, nor does it mean every magnetar is born in a superluminous explosion. The connection is suggestive, not automatic. Several engines can brighten stellar debris, and the early light from a distant explosion can be interpreted in more than one way. This uncertainty makes the rarity question harder. If the visible birthplaces are ambiguous, then the true formation rate has to be inferred indirectly from imperfect traces. There is also a selection problem in the known population. Magnetars are easiest to identify when they are active, and activity fades. A magnetar that no longer produces strong outbursts may be catalogued as a different kind of neutron star, or may not be detected at all. Distance plays a role as well. A magnetar in a nearby region of the Milky Way can reveal itself through bursts or persistent high-energy emission. One in a distant galaxy may only be noticed if it produces an exceptional flare, or if its birth strongly affects the surrounding supernova. The observed rarity is therefore a combination of true rarity and observational bias. The universe may contain more magnetars than the current list suggests, but not enough to make them ordinary. Their active phase is short, their signals are uneven, and their birthplaces can be crowded with other sources of radiation. Counting them is not like counting stable stars. It is closer to reconstructing a population from flashes, remnants, and fading evidence. The comparison with ordinary pulsars shows why this matters. Pulsars can remain detectable through regular radio beams for long periods, as long as their spin, magnetic geometry, and surrounding plasma allow emission to continue. Their regularity makes them easier to survey and classify. Magnetars do not always offer that kind of steady behavior. Some rotate slowly compared with young pulsars, despite being energetic in bursts. Some appear quiet for years before an outburst reveals them. Some may never point their emission toward Earth in a way that makes them obvious. Their identity is tied to magnetic activity, and magnetic activity is not constant. This means the boundary between a magnetar and other neutron stars may be less rigid than the name suggests. There may be objects with magnetar-like internal fields but ordinary external behavior. There may be high magnetic field pulsars that occasionally act like magnetars. There may be old magnetars whose fields have decayed until their violent early history is no longer visible. Rarity, in this sense, is not only about how many are born, it is also about how long they remain recognizable. The deeper issue is that magnetars require several rare conditions to align. The parent star must leave a neutron star rather than a black hole. The remnant must be born with the right mass, rotation, and thermal state. Its interior must amplify or preserve an extreme magnetic field before the crust becomes stable. Its surrounding debris must not hide all evidence of its early activity. Its field must remain strong enough to produce observable signs during the period when astronomers can detect it. Each condition removes some possible objects from the count. None of these filters is impossible, but together they make magnetars uncommon. That uncommonness gives them scientific value. They are not simply stronger versions of ordinary neutron stars. They mark a special outcome of stellar death, one that preserves information about rotation, magnetic amplification, explosion physics, and the limits of compact matter. The question of why magnetars are rare therefore does not reduce to a single missing ingredient. It is a question about how a massive star's final structure, the collapse of its core, the birth spin of the remnant, the internal dynamo, and the surrounding debris all combine in a brief interval. By the time the supernova remnant expands enough to be studied in detail, the critical decision has already been made. The neutron star has either crossed into a magnetic state strong enough to shape its future, or it has settled into a less extreme path. The evidence left behind can be read, but the event itself is gone. This is why magnetars remain important to the study of stellar death. They are rare not because the universe lacks violence, but because only certain violent deaths arrange their conditions precisely enough to leave behind a neutron star ruled by magnetism. A magnetar does not have to begin with the collapse of a single massive star. There is another path, less common to observe and harder to reconstruct, in which the starting point is not one dying star but two neutron stars already formed long before. These objects may spend millions or billions of years orbiting each other after the deaths of their original stars. Each one is already a compact remnant, dense, magnetic, and gravitationally extreme. Over time, their orbit slowly loses energy through gravitational waves, small ripples in space-time that carry energy away from the system. The loss is gradual for most of the binary's life, but it is relentless. The orbit tightens, the stars circle faster, their separation shrinks until the final approach becomes sudden. In the last moments, the two neutron stars are no longer separate in any stable sense. Their surfaces distort under tidal forces. Matter is pulled away. The magnetic fields of both objects are compressed, twisted, and forced into violent contact. Then the two remnants merge. What follows depends on mass, spin, and the behavior of matter at densities beyond the center of an atomic nucleus. The merger can produce a black hole almost immediately. It can also produce a temporary neutron star so massive that it survives only briefly before collapsing. In a narrower set of conditions, it may produce a longer-lived neutron star one rotating extremely quickly and carrying an amplified magnetic field. That object is a natural candidate for a newborn magnetar. This second birth channel is important because it begins with material that is already compact. In a core collapse supernova, a large stellar core has to fall inward and form a neutron star from ordinary stellar matter. In a neutron star merger, the matter is already in the neutron star state. The problem is not how to make dense matter. The problem is what happens when two dense remnants are combined into one. The new object may be heavier than any stable neutron star formed by a single collapse, but rapid rotation can temporarily help support it against gravity. Rotation changes the balance because spinning matter can resist collapse in ways that a non-rotating object cannot. This support is not permanent. The remnant loses rotational energy through gravitational waves, magnetic braking, and winds of particles and radiation. As it slows, the extra support weakens. If the mass is above the true limit for a stable neutron star, collapse into a black hole becomes only a matter of time. That time may be extremely short, but even a short survival can matter. A remnant that lives for fractions of a second, seconds, minutes, or longer may inject energy into the debris around it. If it lives long enough as a Magnetar, it can change the signal that astronomers later see. The merger environment is naturally suited to building strong magnetism. During the final collision, the outer layers of the neutron stars shear against each other. Fluids move at different speeds. Turbulence grows. Magnetic fields can be stretched and folded by that motion. In physical terms, the merger creates conditions where small fields can be amplified rapidly by instabilities in the dense matter. The remnant is also rotating at a tremendous rate, because the orbital motion of the binary has been converted into spin and internal motion. This means that the same ingredients considered important in single-star Magnetar formation appear again, but in a different form. There is rapid rotation. There is hot, unstable matter. There is magnetic field already present before amplification begins. There's also an enormous supply of gravitational energy released in a very small region. The result, at least in some models, is a newly merged neutron star whose magnetic field can reach Magnetar strength very quickly. It may not look like the Magnetars identified later inside the Milky Way, because it is buried inside merger debris and surrounded by ejecta moving outward at high speed. But its central engine may be Magnetar-like from the beginning. Around the remnant, the collision throws out neutron-rich matter. Some of it is expelled dynamically during the merger itself, pulled out by tidal forces and squeezed out by shock heating. More material may leave later in winds from a hot accretion disk surrounding the central object. This ejecta is important because it produces a kilonova, a transient glow powered by the radioactive decay of heavy elements formed in the neutron-rich material. A kilonova is not simply a smaller supernova. Its source of light is different, its timescale is shorter, and its material can be rich in elements made by rapid neutron capture. In a merger without a long-lived central engine, the kilonova fades as the radioactive heating declines and the debris expands. But if a Magnetar survives at the center, it can add energy. Its rotation and magnetic field can drive a wind that pushes into the ejecta, heats it, accelerates it, and changes how bright it becomes. The light from the merger may therefore carry an imprint of the remnant's lifetime. If the central object collapses almost immediately, the imprint may be weak or absent. If it survives longer, the debris can remember that extra energy. This is why neutron star mergers offer a possible way to study Magnetar formation indirectly. The Magnetar itself may be hidden, but the surrounding matter can respond to it. The difficulty is that the same event contains several overlapping signals. A short gamma-ray burst may be produced if a narrow jet forms and points toward Earth. The kilonova may glow in optical and infrared light as heavy elements decay. The afterglow may emerge when the jet interacts with surrounding gas. A magnetar-driven wind may add power to the ejector. Later still, the energized material may produce radio emission as it sweeps up interstellar matter. Each signal depends on viewing angle, environment, mass, and remnant lifetime. No single observation gives a complete answer. A bright kilonova might suggest extra energy, but it might also reflect ejector mass or opacity. A long-lasting high-energy signal might suggest a central engine, but it may have more than one possible explanation. A late radio signal could point toward magnetar-boosted ejector, but only if it can be separated from other sources of emission. The evidence has to be assembled carefully, with each piece constrained by the others. The possibility of a merger-born magnetar also connects to the maximum mass of neutron stars. There is a limit beyond which dense matter cannot support itself against gravity. The exact value is still uncertain because it depends on the equation of state, the relation between pressure and density inside neutron star matter. Observations of heavy neutron stars help narrow this limit, but they do not fully settle what happens in the hottest and fastest rotating merger remnants. A newly merged object may be called hypermassive if it is supported by rapid and uneven rotation, but must collapse quickly once that support is lost. It may be called supramassive if uniform rotation can support it for longer, until spin down removes enough support for collapse. It may be stable if its mass is below the non-rotating limit. These categories are not just labels, they describe different lifetimes, and lifetime is central to the magnetar question. A stable remnant could inject a very large amount of rotational energy into the ejector. A supramassive remnant could inject less before collapsing. A hypermassive remnant might leave only a brief and subtle trace. The same merger can therefore produce very different observable outcomes depending on where the remnant falls relative to the mass limit. This second birth channel is attractive because it explains how extreme magnetism could arise from an already extreme collision. It also gives astronomers a reason to search the aftermath of mergers long after the first flash has passed. A magnetar born in a merger may not remain visible as a clean point source. It may collapse before it can be directly identified. Its magnetic field may release energy into debris rather than into a steady beam. Its best evidence may appear as an altered kilonova, an extended gamma-ray signal, or delayed radio emission years later. This makes the object both powerful and elusive. It can change the event around it without surviving long enough to be seen on its own. The idea also broadens the meaning of magnetar formation. Some magnetars may be born from the collapse of massive stars. Others may be assembled from the remnants of stars that died long before. In one path, a single core falls inward. In the other, two compact cores complete a long orbital decay and merge. Both routes lead to the same deeper question. Under what conditions can nature produce a neutron star whose magnetic field becomes the main source of its energy? The merger path does not replace the collapse path. It adds another possible doorway, one in which the magnetar's life may be especially short, not because the field is weak, but because the remnant carrying it is too massive to endure. The object may be born spinning, magnetized, and surrounded by debris, yet already close to the edge of collapse. Its existence may be temporary from the first moment. What matters is whether that temporary life lasts long enough to leave a measurable trace. Kilonova debris does not finish its work when the first glow fades. In the early days after a neutron star merger, the ejector expands rapidly, cools, and shines because unstable heavy elements inside it are decaying. That light can rise and vanish quickly compared with a supernova, leaving behind a region that may look quiet long before the physical consequences of the collision have ended. The debris is still moving outward. It still carries mass, speed, and memory of whatever happened at the center. If the merger produced a black hole almost at once, the ejector may expand mostly with the energy it gained during the collision and from radioactive heating. If the merger produced a magnetar that survived for a longer time, the story changes. The central remnant can inject rotational energy into the surrounding material, pushing it outward harder than the merger alone would have done. The effect may not be most visible at the beginning. The earliest light is crowded with overlapping signals, and the central object is buried beneath expanding material that absorbs, scatters, and reprocesses radiation. The magnetar may be present, but not exposed. Its evidence can be delayed until the energized debris reaches a larger scale and begins to interact with the medium around it. This delayed evidence is one reason radio observations matter. The expanding ejector from a kilonova moves through interstellar gas, the thin material between stars. As it travels, it sweeps up that gas. At first, the swept-up mass is small compared with the mass of the ejector, so the debris continues outward with little change. Over time, however, the amount of encountered material grows. When enough mass has been swept up, the ejector begins to slow more significantly, and energy is transferred into the surrounding particles. Electrons are accelerated. Magnetic fields in the shocked region help those electrons emit synchrotron radiation, a type of radiation produced when fast-charged particles spiral through magnetic fields. Synchrotron emission is common in high-energy astrophysics, but the important detail here is its timing. For a magnetar-boosted kilonova, the radio signal may rise years after the merger, not minutes, hours, or days later. The event that created the remnant is over, but the debris has only then reached the stage where its stored energy becomes readable in radio light. The timing depends on several connected quantities. One is the mass of the kilonova ejector. A more massive shell has more inertia and may take longer to slow down. Another is the speed of the ejector. Faster material reaches a given radius sooner and carries more kinetic energy into the surrounding gas. A third is the density of the environment. If the merger occurs in a relatively dense region, the ejector sweeps up significant mass sooner, so the radio signal may peak earlier and more brightly. If it occurs in a thin environment, the same process can take longer and may produce a fainter signal. This dependence makes the delay useful but difficult. A missing radio detection does not mean the same thing in every environment. It may mean that no long-lived magnetar added much energy. It may also mean that the surrounding gas is too thin, the ejector is slower than expected, or the signal has not yet reached its peak. The interpretation has to be built from models, distance, observation time, and sensitivity. Still, the delayed radio search has one valuable advantage. It looks for the mechanical consequence of energy injection. Instead of trying to see the central object directly, it asks whether the material around it was accelerated beyond what a normal kilonova would allow. If a newborn magnetar deposited a large fraction of its rotational energy into the ejector, that ejector should carry the effect outward. Later, when it strikes the surrounding medium, it should produce a radio afterglow brighter than one powered only by the original merger debris. This is why the absence of radio emission can matter. It can limit how much energy was added, which in turn limits how long the central neutron star could have survived and how rapidly it could have spun down. The radio sky becomes a delayed test of the remnant's hidden life. The signal being sought is not the same as the prompt gamma-ray burst, and it is not exactly the same as the early afterglow from a narrow jet. A gamma-ray burst, when present, comes from a highly energetic outflow directed into a narrow beam. If that beam points near Earth, it can appear bright and brief. The jet afterglow follows as the jet slows in surrounding material. A magnetar-boosted kilonova, by contrast, can be much less directional. The ejector spreads over a wider range of angles, closer to a broad outflow than to a tight beam. This matters because many neutron star mergers may not point their jets toward Earth. Their gamma rays may be missed or appear weak, but if a magnetar adds energy to the ejector in a more general way, the later radio emission could be visible from a wider set of viewing angles. That makes it a useful target for surveys as well as for follow-up observations of known bursts. It gives astronomers a way to search for central engines even when the first signal was incomplete or geometrically unfavourable. The delay also changes the emotional shape of the science. Many transient events demand immediate action. A supernova is found, and telescopes turn quickly to catch the rise, the peak, and the early fading. A gamma-ray burst is detected, and follow-up begins as soon as possible because the afterglow can fade rapidly. Kilonovae also require fast observation in optical and infrared light, since their early glow changes from day to day. But the radio signature of energized ejector asks for patience. The important observation may come after the event has left the news cycle, and after the first papers have already described the early behavior. It may require returning to a patch of sky years later, when the original source seems inactive by ordinary standards. This is not a weakness of the method, it is part of the physics. The ejector has to travel, it has to gather enough surrounding matter, it has to convert bulk motion into particle energy and radiation. The clock is set not by human attention, but by expansion through space. A Magnetar remnant can therefore leave more than one kind of imprint. In the first moments, it may affect high energy emission if it survives long enough to power extended activity. In the first days, it may alter the brightness and color of the kilonova by heating the ejector from within. In later years, it may reveal itself through radio emission from accelerated debris. Each stage tests a different part of the same event. Early light tests the composition, opacity, and heating of the ejector. Gamma rays test jet formation and central engine behavior. Late radio emission tests kinetic energy and interaction with the environment. A consistent picture has to respect all of them. If one stage suggests a long-lived magnetar while another strongly limits the available energy, the model has to change. The strength of this approach is that it does not depend on a single dramatic sign. It builds a case through the debris, reading the remnant by what it did to the material around it. This is especially important because a newly formed magnetar in a merger is not guaranteed to survive. If it collapses into a black hole after a short time, direct detection may be impossible. The collapse could occur while the remnant is still buried. The signal from the central object could be absorbed or blended with other emission, but the energy it released before collapse may remain in the ejector. A remnant that lived only briefly could still leave a measurable difference between ordinary merger debris and boosted debris. The challenge is to decide how much difference is enough. Theoretical models can estimate the radio brightness expected for different energies, masses, velocities, and environments. Observatories can then test those expectations. A detection would be important, but even a non-detection can narrow the permitted range. The debris either carries the energy or it does not, and careful radio limits can make that statement quantitative without requiring the magnetar to be seen directly. In this way, the kilonova becomes more than a fading glow. It becomes a delayed messenger from the hidden center of the merger. The material thrown outward is not passive. It records the energy budget, carries it into surrounding space, and eventually turns part of it into radiation that radio telescopes can measure. The delay is not a failure to observe quickly enough. It is the time needed for the evidence to mature. A magnetar born in a merger may live briefly, collapse quietly, and leave no stable remnant to identify. Yet if it gave enough energy to the ejector, The expanding debris should continue the testimony after the central object has changed or disappeared. The question becomes not only what happened at the moment of collision, but how long the wreckage remembers it. GRB 211211. A did not settle neatly into the usual categories. It arrived as a gamma-ray burst, a sudden flash of high-energy radiation from a distant cosmic explosion, and at first its duration pointed toward a familiar interpretation. Gamma-ray bursts are often divided by how long the gamma rays last. Short bursts, lasting less than about 2 seconds, are usually linked to compact object mergers, especially neutron stars. Long bursts, lasting more than about 2 seconds, are usually linked to the collapse of massive stars, where a dying stellar core forms a compact central engine and drives a relativistic jet through the surrounding star. This division is not perfect, but it has been useful because duration often reflects the kind of object feeding the jet. GRB2 11211A was different. Its gamma-ray emission lasted far longer than the short-burst boundary would suggest. Yet the rest of the evidence did not behave like a normal massive star collapse. The event became important because it forced two normally separate pictures to overlap. It looked long in gamma rays, but in other wavelengths it carried the signs of a merger. That mismatch is the reason it became a valuable test case for the idea of a magnetar born from colliding neutron stars. A long burst from a massive star should often be followed by a particular kind of supernova. When the core collapses and the jet escapes, the outer layers of the star are disrupted, and the expanding debris can produce a bright optical display over days and weeks. Astronomers know what to look for in that case. They search for the rising and fading light of the supernova, its colour, and the way its spectrum changes as the ejector expands. For GRB 211211A, that expected supernova was not found. This absence mattered because the burst was relatively nearby by gamma-ray burst standards, making follow-up observations more capable of detecting faint emission. If a standard core collapse supernova had accompanied the event, it should have been difficult to hide. Instead, observers found a red transient, meaning a source that was brighter at infrared wavelengths than in ordinary optical light, and that redness appeared earlier than would be expected for a typical supernova. The colour and timing pointed away from a normal massive star death and toward a different source of light. The closest comparison was a kilonova, the glow produced when neutron-rich matter from a compact merger expands and forms heavy elements. A kilonova does not shine like a normal supernova because its material is different. The debris from a neutron star merger can be filled with heavy nuclei made by rapid neutron capture, a process in which atomic nuclei absorb neutrons quickly before they have time to decay. These heavy elements affect how light escapes. They can make the emission redder, especially when the ejector contains lanthanides, a group of heavy elements with many ways to absorb and re-emit light. In the known neutron star merger associated with gravitational waves, the kilonova showed this shift from bluer early light to redder infrared emission as different ejector components emerged. GRB 211211A appeared similar enough to raise a serious possibility despite its long gamma-ray duration. It may have come from a neutron star merger rather than a massive star collapse. This did not erase the duration problem, it sharpened it. If a merger caused the burst, then something had to explain why the gamma rays lasted so long. One possible answer is a central remnant that did not collapse immediately. In many neutron star merger models, the two stars combine and form a black hole either promptly or after a short delay. A black hole with an accretion disk can power a jet, but if the remnant collapses quickly, the engine may not last long. If instead the merger leaves behind a massive neutron star for a longer interval, the engine can continue injecting energy. If that neutron star is rapidly rotating and strongly magnetized, it enters the range of a magnetar or magnetar-like remnant. Its spin and magnetic field can drive extended emission after the first spike of gamma rays. In this picture, the unusual duration of GRB 211211A is not a mistake in classification. It is a clue to the lifetime of the central object. The gamma rays may be telling part of the story of a neutron star that survived long enough to keep the engine active, even if it later collapsed into a black hole. The case would have been easier if gravitational waves had been detected at the same time. Gravitational wave observatories can measure the ripples from merging compact objects, giving direct evidence that neutron stars or black holes were involved. For this event, that confirmation was unavailable. The detectors were not in an observing period, and the source distance would have made detection challenging even under favourable conditions. Without gravitational waves, the interpretation had to rely on electromagnetic evidence gamma rays, optical light, infrared emission, and later searches at other wavelengths. This makes the event less clean than a merger detected by both light and gravitational waves, but not less useful. In astronomy, many important objects are understood through incomplete evidence. The strength of the case comes from how well different observations support or resist each interpretation. For GRB 211211A, the absence of a supernova and the presence of kilonova-like infrared emission created a strong argument that the long burst did not come from the usual massive star channel. The event also showed why the old short and long division cannot be treated as a strict law. Duration is a helpful sign, but it is not the physical cause. A burst is long or short because of how the central engine behaves, how the jet forms, and how energy escapes. A massive star collapse can power a long burst because the engine may be fed by collapsing stellar material for an extended time. A merger usually gives a shorter burst because the available accretion and engine activity may be briefer. But if a merger produces a long-lived magnetized neutron star, the engine can last longer than expected. The duration then begins to resemble the massive star category, even though the origin is different. This is why GRB 211211A is not merely an exception. It is a warning that the surface behavior of an explosion can imitate another class when the central engine follows a different path. Classification has to be tied back to physical origin, not only to a measured timescale. For the Magnetar question, the event was especially valuable because it had several favourable features at once. It was close enough to allow deep follow-up compared with most gamma-ray bursts. It showed evidence consistent with a kilonova. It lacked the expected supernova of a massive star collapse. It also appeared to occur in an environment dense enough that late radio emission, if strongly powered by Magnetar-boosted ejector, might become detectable on timescales of years rather than much longer intervals. That made it a natural target for radio observations. If the merger produced a long-lived Magnetar, and if that Magnetar deposited a large amount of rotational energy into the ejector, the expanding debris should eventually interact with surrounding gas and produce a bright radio signal. The same object that created confusion in gamma rays therefore became a useful test case in radio. Its early behavior raised the possibility of a Magnetar remnant. Its later behavior could test how much energy that remnant actually gave to the ejector. This is the careful sequence that makes the case scientifically strong. The long gamma-ray signal opens the question. The missing supernova removes one likely answer. The red transient supports a merger origin. The kilonova interpretation allows a central remnant. The possible remnant suggests Magnetar energy injection. The radio follow-up then asks whether that energy injection really happened at the expected scale. Each step is uncertain on its own, but together they form a path from observation to constraint. The event does not require a Magnetar in order to be interesting. It is already important because it blurs a boundary that had been treated as useful for many years. But if a Magnetar or temporary Magnetar-like object formed at its centre, The event becomes more than a classification problem. It becomes a direct test of how neutron star mergers can produce short-lived central engines. GRB2 11211A therefore sits between several questions. What makes a gamma ray burst long or short? How can a neutron star merger imitate part of the behavior of a massive star collapse? How often do mergers leave behind a neutron star instead of forming a black hole immediately? And how much energy can that remnant deliver before it collapses or quiets? The answers are not contained in the first flash alone. They are distributed through the missing supernova, the infrared colour, the fading afterglow, and the late radio limits. The burst did not provide a simple discovery of a magnetar. It provided something more cautious and more useful, a case where the usual categories were strained enough that the hidden remnant had to be taken seriously. Searching the afterglow begins with a change in attention. The first light of a merger is urgent, but the late radio search is patient by design. After the gamma rays have ended, after the optical source has reddened and faded, and after the infrared glow has slipped below ordinary detection, the debris is still moving through space. It is no longer a bright transient in the usual sense. It is an expanding shell carrying the energy of the collision, and perhaps also the energy of a central remnant that survived long enough to change it. Radio telescopes enter the story at this quieter stage because they can test the motion of that debris rather than the first heat of the explosion. The signal they seek is not a direct image of a magnetar, it is a consequence. If a magnetar formed at the centre and poured rotational energy into the kilonova ejector, the material should have been accelerated. Later, as that faster material ploughs into the surrounding medium, it should disturb electrons and magnetic fields in a way that produces synchrotron radiation. The radio observation is therefore an indirect question written in physical form: how much energy was the ejector carrying when it reached the gas around the merger? This makes the search both powerful and difficult. A newborn magnetar can be hidden, collapsed, or impossible to separate from other early emission. But the debris it energized cannot easily erase its history. It carries that history outward until interaction with the environment makes it measurable. If the signal is bright enough, and if telescopes look at the right time, the method depends on understanding what radio telescopes are actually measuring. They do not see the shell as a simple solid edge. The ejector is diffuse, expanding, and far too distant to resolve in detail for most events. What can be measured is brightness at radio frequencies, and how that brightness changes with time. When fast ejector sweeps up surrounding gas, a shock forms. In that shocked region, electrons are accelerated to high energies. Magnetic fields guide their motion. As the electrons spiral, they emit synchrotron radiation, which can appear as a radio source that brightens, peaks, and fades. The shape of that rise and decline contains information. A bright early peak can suggest dense surroundings or energetic ejector. A late faint peak can suggest thinner surroundings or slower material. No interpretation is automatic, because several combinations of mass, speed, energy, and density can produce similar radio behavior. But a sensitive non-detection can still remove some possibilities. If the predicted signal from a strongly boosted kilonova should have been visible, and no signal is found, then the model has to give up some of its allowed energy, density, or remnant lifetime. For events like GRB2 11211A, this is why follow-up years after the burst matters. The early evidence made a magnetar remnant plausible. The radio sky could then ask whether the remnant had enough time to power the ejector at the level expected for a long-lived magnetar. The instruments used for this work are built for faint, careful measurements. The Very Large Array in New Mexico is not a single telescope but a system of radio antennas spread across the desert, working together as an interferometer. An interferometer combines signals from separated antennas so they act like a much larger instrument, improving the ability to locate and measure faint radio sources. Meerkat in South Africa works in a similar broad tradition, using many dishes together to produce sensitive radio images of the sky. These observatories are valuable because the expected signals from merger debris can be weak, especially when the event is distant or the surrounding gas is thin. A radio follow-up program therefore has to be planned around sensitivity, frequency, timing, and comparison with earlier observations. The astronomer is not simply looking for any radio point at the position of the burst. The measurement has to separate possible merger emission from background galaxies, unrelated sources, and the fading afterglow of any jet. It also has to account for the fact that the same region of sky may contain older radio sources that do not belong to the explosion. A late detection is meaningful only if it changes in a way that matches the expected transient behavior, or if previous images show that it was not there before. This careful comparison is what turns a faint radio measurement into evidence about a hidden central engine. The search is shaped by the expected difference between ordinary kilonova ejecta and Magnetar boosted ejecta. In a merger that promptly forms a black hole, the ejecta still has kinetic energy from the collision. It can still produce a kilonova afterglow at late times as it interacts with surrounding material. But the energy scale is lower than it would be if a long-lived magnetar transferred a large amount of rotational energy into the debris. A stable or long-lived magnetar could, in principle, add enough energy to make the later radio emission much brighter. A remnant that collapses quickly would have less time to do so. This creates a ladder of possibilities. At the high end is a remnant that survives and injects a very large amount of energy. Below that is a remnant that lives briefly, adds some energy, and then collapses. Lower still is the case where the merger forms a black hole promptly, leaving only ordinary kilonova ejecta. Radio observations try to determine where along this ladder an event belongs. A strong detection could place the ejecta high. A deep non-detection can push it downward. The result may not identify the remnant by name, but it can make certain lives too energetic or too long to remain plausible. For GRB 211211A. The interest was sharpened by its unusual early behavior. Its long gamma-ray emission suggested a central engine that did not shut off immediately, while the kilonova-like light suggested a compact merger. If that engine was a magnetar, the late radio emission might have carried the signature of its spin down. Spin down means the loss of rotational energy over time, often through magnetic fields and particle winds. In a Magnetar remnant, that lost rotational energy does not simply vanish. Some of it can be transferred into the surrounding ejecta. The expected consequence is faster, more energetic material, and a brighter radio signal once the ejecta begins to slow in the external medium. Observations with sensitive radio arrays therefore become a test of how generous the central engine could have been. If the radio source is absent at a time when a powerful Magnetar model predicts it should be present, then a long-lived remnant becomes less likely. The conclusion is cautious because models depend on the density around the merger and the exact properties of the ejecta. But caution does not make the result empty. It gives the non-detection a measured meaning. The hidden object either failed to survive long enough, failed to transfer enough energy, or existed in conditions that made the radio signal too faint to see. There is a quiet discipline in this kind of astronomy. The most important result is not always a new bright source appearing in an image. Sometimes it is a clean limit, a careful statement that something brighter than a certain level was not present. Such a limit can be disappointing in the ordinary sense, because it does not deliver the object being sought. But scientifically, it can be valuable. It removes the easiest version of a model. It says that if a magnetar formed, It was not a stable remnant pouring a maximal amount of energy into the ejector under the assumed conditions. It may have collapsed. It may have been weaker. It may have lost energy through channels that did not strongly boost the debris. These alternatives are less direct than a detection, but they are not vague. They narrow the remnant's possible life. The afterglow search, therefore, does not only look for magnetars. It tests how long they can remain alive after a merger, how much spin energy they can share with their surroundings, and how often a neutron star merger avoids prompt collapse. The radio image becomes a late examination of the central engine after the engine itself may no longer exist. This is why searching the afterglow is essential to the larger story. A magnetar's birth can be hidden inside explosive light, and its death can occur before any telescope has a clear view of it. But the debris around it expands into a broader and slower record. It turns the central question into something that can be revisited. Years after the burst, the same patch of sky can still be tested. The absence or presence of radio emission can still shift the interpretation. The first flash may have raised the possibility of a magnetar, but the afterglow decides how much of that possibility survives contact with the surrounding medium. What remains is not a simple hunt for a visible remnant. It is a search for energy that should have been left behind if the remnant lived long enough to matter. The meaning of a non-detection depends on what the search was capable of seeing. In ordinary language, finding nothing can sound like the end of an inquiry, but in observational astronomy it can become a measurement of what the universe did not allow under certain conditions. For GRB 211211A, the late radio search did not reveal the bright emission expected from a strongly magnetar-boosted kilonova. No clear radio source appeared at the position with the brightness required by the most energetic versions of the model. That result does not prove that no neutron star remnant ever existed at the centre. It does not prove that the merger formed a black hole instantly. It does not remove every possible magnetar scenario. What it does is narrower and more useful. It says that if a magnetar-like remnant formed, it could not have deposited a very large amount of rotational energy into the ejector in the way a long-lived, stable remnant would be expected to do under the modelled conditions. The absence becomes a boundary. It turns a wide possibility into a smaller one. Before the observation, the event allowed a range of central engines. After the observation, some of the most energetic versions became harder to keep. This is how nothing becomes evidence not by replacing a detection, but by closing off part of the space where explanations were allowed to live. The key idea is energy. A newly merged neutron star can contain an enormous reservoir of rotational energy if it is born spinning rapidly. If it also has a magnetar strength field, that field can help drain the spin energy and transfer some of it into winds, radiation, and the surrounding ejector, a stable remnant, one whose mass is low enough to remain a neutron star indefinitely, could release a very large amount of this energy over time. In simplified terms, it could act like a long-lasting engine inside the debris. The ejector would then expand faster and carry more kinetic energy than it would have carried from the merger alone. When that energized material later struck the surrounding gas, it should have produced a stronger radio afterglow. If the predicted radio brightness lies well above the limits reached by the telescope, and the telescope still sees nothing, the model has to change. The remnant cannot be both long-lived and efficient at transferring that much energy into the ejector, at least not in the environment assumed for the calculation. That conclusion is not dramatic, but it is physically sharp. It connects the missing radio source to the lifetime and behavior of an object too hidden to observe directly. For GRB2 11211A, the constraint falls in the range that distinguishes different remnant outcomes. A stable neutron star would be expected to inject energy on the order of 10 to the 53 ergs, depending on its spin and magnetic field. A remnant above the stable mass limit, but temporarily supported by rotation, would have less time. It might add energy somewhere around 10 to the 52 to 10 to the 53 ergs before slowing enough to collapse into a black hole. The radio observations placed limits around a few times 10 to the 52 ergs for the energy that could have gone into the kilonova ejector. In plain terms, the debris did not look as if it had received the full push expected from a permanently surviving magnetar. If a neutron star formed in the merger, the evidence favours a remnant that lived temporarily and then collapsed, rather than one that stayed behind as a stable magnetar. This does not make the event unimportant. It gives the event a more precise shape. The possible magnetar, if present, was not a long-lived survivor. Its life was constrained by the energy it failed to leave in the expanding material. That kind of conclusion rests on models, and those models have limits. The radio brightness depends not only on the engine, but also on the density of the surrounding medium. If the merger occurred in a very thin environment, even energetic ejector could produce weaker emission than expected. The brightness also depends on how efficiently the shock accelerates electrons and amplifies magnetic fields, and on the mass and velocity structure of the ejector. These quantities are not always known with precision. Astronomers therefore do not read a non-detection as a simple yes or no answer. They ask what combinations of assumptions remain possible. A dense environment and a powerful magnetar may be ruled out together, while a thinner environment and a weaker or shorter-lived remnant may still survive. The result is a map of allowed and disallowed conditions. It is less satisfying than seeing a bright radio source appear exactly where predicted, but it is often more honest. The universe does not always answer in the form most convenient for classification. Sometimes it answers by refusing to match the strongest version of an idea. The value of the null result becomes clearer when it is compared with the early clues from the same event. The long gamma-ray emission suggested that the central engine may have lasted longer than in a standard short burst. The red kilonova-like transient suggested that the origin was a compact merger, rather than the collapse of a massive star. Together, those clues made a magnetar remnant plausible, but plausible is not the same as demonstrated. A central engine can produce extended emission without necessarily leaving a stable neutron star. A merger can produce unusual gamma rays and still collapse into a black hole after a short delay. The late radio non-detection presses against the most energetic interpretation and asks whether the remnant really had enough time to load the ejector with a large amount of spin energy. The answer appears to be no, at least for the simplest strong magnetar boosted model. This is the importance of returning to the event years later. The early data opened the door. The late radio data narrowed the corridor behind it. Nothing in the radio image changed the fact that GRB2 11211A was unusual. It changed what kind of unusual object it could most easily have been. Non-detections also help with population questions. One event can be explained in many ways, but repeated failures to find bright magnetar-boosted radio emission from merger candidates begin to shape the broader picture. If stable magnetar remnants were common after neutron star mergers, and if they usually transferred large amounts of energy into their ejector, radio searches should eventually begin to find them. If those searches keep producing only upper limits, the simplest conclusion is that many mergers do not leave stable neutron stars. They may form black holes promptly, or after a short temporary phase. This fits with mass arguments from known binary neutron stars, where the combined mass often appears high enough that a merger remnant may exceed the stable neutron star limit. The exact limit remains uncertain, because dense matter at these pressures is not fully understood. But each non-detection adds pressure to the idea that long-lived merger remnants are not the normal outcome. The absence of a bright radio signal becomes part of a larger statistical pattern. It helps estimate not just what happened in one event, but how often certain remnants survive across the universe. This is why the phrase null result can be misleading if it is heard as a failure. The observation may fail to find the desired source, but it can succeed at testing a physical claim. In this case, the claim is that a long-lived Magnetar remnant should energize the kilonova ejector enough to produce late radio emission at a detectable level. When that emission is not seen, the claim is weakened or forced into a narrower set of conditions. The telescope has still measured the sky, the limit has still been set, the model has still been challenged. This is a normal part of how science approaches objects that cannot be handled directly. A magnetar in merger debris is too distant, too small, and too hidden to inspect. Its life must be inferred from energy, timing, and material response. A non-detection is one of the tools that makes that inference possible. It tells researchers where not to search for the answer, or at least which version of the answer has become less likely. The result also preserves the central tension of magnetar formation. The event still looks like a compact merger with unusually long gamma-ray activity. It still suggests that the central engine may not have ended immediately, but the radio limits argue against a remnant that lived as a powerful stable magnetar and strongly accelerated the ejector. The most balanced interpretation lies between those points. A massive neutron star may have formed and survived briefly. It may have powered some extended emission. It may have lost support as it spun down and then collapsed into a black hole before it could leave the full radio signature of a stable magnetar. In that picture, the magnetar's life is not denied. It is shortened. Its evidence is not a visible survivor, but a set of constraints around missing energy. The violent life becomes brief enough that the debris carries only a limited trace. What remains is a careful kind of absence, one that does not close the mystery but gives it firmer edges. A merger remnant can be born already close to failure. When two neutron stars combine, the new object may have more mass than any cold, non-rotating neutron star can support. For a brief time, collapse can be delayed by rotation, thermal pressure, and the uneven distribution of matter inside the remnant. These supports are real, but they are temporary. Heat escapes through neutrinos. Differential rotation, where different layers spin at different rates, is smoothed by magnetic fields and internal friction. Gravitational waves can carry away energy and angular momentum. Magnetic winds can drain the spin. Each process removes part of the support that keeps the remnant from becoming a black hole. This is the reason a merger-born magnetar can have a short life from the moment it forms. Its magnetic field may be strong enough to power emission, twist the surrounding plasma, and transfer energy into the ejector, while its mass may be high enough that survival is never secure. The remnant is balanced on rotation, and rotation is being lost. The collapse into darkness, if it comes, is not a second explosion in the ordinary sense. It is the end of support. The dense matter crosses the point where pressure and spin can no longer resist gravity, and an event horizon forms around what had just been a neutron star. This possibility matters because it links magnetar behavior to the maximum mass of neutron stars. That maximum is not known exactly. It depends on the equation of state, the rule that describes how dense matter responds when squeezed to pressures far beyond ordinary nuclei. Observations of heavy pulsars show that neutron stars can reach at least around twice the mass of the Sun, but the precise upper boundary remains under study. Mergers test that boundary in a different way. They assemble an object that may exceed the stable limit, then reveal its fate through gravitational waves, gamma rays, kilonova light, and delayed emission. If collapse is prompt, the remnant becomes a black hole almost immediately, and the central engine behaves differently. If collapse is delayed, a massive neutron star exists long enough to affect the surrounding debris. There are several possible stages between survival and immediate collapse. A hypermassive neutron star is supported by differential rotation and thermal pressure, and it may last only a very short time before collapsing. A supramassive neutron star is supported by uniform rotation and can survive longer, but only while it spins fast enough. A stable neutron star remains below the mass limit even without extra rotational support. These categories are important because they imply different amounts of energy can escape before the final state is reached. A hypermassive remnant may have little time to power the ejector. A supramassive remnant can inject more energy before spin down removes its support. A stable remnant may leave the strongest long-term imprint. The challenge is that all three outcomes can begin in the same violent merger environment. The difference may lie in a small margin of mass, rotation, and dense matter physics. A remnant only slightly above the stable limit may live long enough to shape the kilonova. A remnant farther above it may disappear before it leaves a clear sign. The collapse itself can be difficult to catch. Some models connect sudden endings in high energy emission to the moment when a temporary neutron star becomes a black hole. If a Magnetar-like remnant is powering an X-ray plateau or extended gamma-ray emission, then a sharp shut-off may indicate that the engine has collapsed. The logic is direct. A spinning magnetized neutron star can keep injecting energy. A black hole formed without the same surrounding conditions may end that specific supply, but the interpretation is not unique. Jets, disks, viewing angle, and surrounding material can also shape light curves. A sudden drop is suggestive. Not a direct view of collapse. Still, it gives astronomers a way to connect timing with remnant lifetime. If the high-energy signal continues for a while and then fades abruptly, the remnant may have survived long enough to act as an engine, but not long enough to become stable. That intermediate possibility is central to the short, violent life of a merger-born Magnetar. The object may exist, act, and vanish before any telescope can isolate it as a separate star. In this setting, a black hole is not simply the opposite of a Magnetar. It can be the Magnetar's final state. A merger may first create a massive, highly magnetized neutron star, then allow it to collapse after some of its spin energy has been released. The early remnant can influence the gamma rays. It can heat or accelerate ejector. It can leave limits in late radio observations. Then, when rotation slows enough, the same object can pass beyond the neutron star limit. This sequence helps reconcile mixed evidence. An event may show signs of a central engine that lasted longer than a prompt black hole would suggest, while also failing to show the strong late radio signature expected from a stable magnetar. The remnant in that case is neither absent nor enduring. It is temporary. Its life is long enough to matter, but too short to leave the full evidence of survival. This is why non-detections do not merely remove Magnetars from the picture. They often push the interpretation towards shorter lifetimes, lower energy injection, or faster collapse. The fate of the remnant also affects the material around it. A stable or long-lived Magnetar can drive winds that inflate a nebula inside the ejector, add heat, and potentially change the kilonova's brightness and color. A remnant that collapses early may leave the ejector closer to the ordinary merger expectation, though not necessarily unchanged. The transition to a black hole can also alter the central environment. Material that once orbited or surrounded the neutron star may settle into an accretion disk, and that disk can continue to feed a jet for a time. The final signal is therefore a combination of several engines turning on and off at different moments. First comes the merger and the violent ejection of matter. Then may come a temporary Magnetar phase, draining spin and magnetic energy. Then may come collapse, followed by whatever emission the black hole and disk can still produce. Collapse into a black hole also has a quieter consequence for the Magnetar population. If many neutron star mergers produce remnants above the stable mass limit, then many merger-born Magnetars may be brief by nature. They would not appear later as isolated galactic magnetars. They would not be found as long-lasting point sources in the remnants of old kilonovae. Their evidence would be transient, indirect, and easy to miss. This could explain why the search focuses so heavily on afterglows, energy injection, and delayed emission rather than on finding a surviving magnetar after the debris clears. The object may no longer exist by the time the surrounding cloud becomes transparent enough for a direct search. Its magnetic field may have been extraordinary, but the field belonged to matter that crossed into a black hole. From the outside, the long-term remnant is not a magnetized surface but a gravitational boundary. The Magnetar phase becomes a temporary chapter inside the formation of something darker and more permanent. This does not make the Magnetar less important. It makes its lifetime the central measurement. Between these possibilities lies the information astronomers are trying to extract. The absence of bright radio emission in a case like GRB2-11211A suggests that the remnant, if it was a magnetar, did not have the long, stable life needed to deliver the largest expected energy. The collapse may have come before the ejector was strongly boosted. The magnetic field may have been intense, but intensity alone could not prevent gravity from winning once rotation declined. The short, violent life therefore has two clocks. One clock measures magnetic activity, the release of stored field energy through radiation, winds, and stress. The other measures gravitational survival, the time before mass overwhelms support and the remnant collapses. In an ordinary magnetar formed by a single supernova, the second clock may not be urgent if the neutron star is stable. The object can spend thousands of years cooling, bursting, and slowly losing magnetic energy. In a merger-born Magnetar, the second clock may dominate from the start. The remnant may be born with a field strong enough to influence the universe around it, while also carrying too much mass to remain a neutron star for long. The end is not decided by how bright it is, but by whether dense matter can continue to hold itself up when it cannot. The Magnetar's visible possibilities narrow suddenly. What survives is not the object as a magnetar, but the trace it left before collapse. That trace may be a longer burst, a changed kilonova, a missing radio signal that limits its power, or a pattern across many events showing that stable remnants are uncommon. Collapse into darkness is therefore not only an ending, it is a filter through which Magnetar formation must pass, deciding whether the remnant becomes a lasting neutron star or only a brief magnetic interval between merger and black hole. Magnetars are not studied only through their birthplaces, they are also studied through the many ways they disturb their surroundings after birth, sometimes as steady high-energy sources, sometimes as sudden bursters, and sometimes as possible engines hidden inside explosions that look too bright or too unusual for a simple model. In the Milky Way, known magnetars are usually identified through X-ray and gamma-ray activity, rather than through ordinary radio pulsations. Some produce repeated short bursts. Some brighten in outbursts and then fade over months or years. Some show pulse periods of several seconds, slower than many young pulsars, while still producing radiation that cannot be explained by rotational energy alone. This is one of the clearest signs that their main energy supply is magnetic. A normal pulsar spends its spin energy gradually. A magnetar can release stored magnetic energy in irregular episodes. And those episodes make it visible even when its rotation is not energetic enough to power the observed emission. Galactic magnetars therefore provide the local examples that anchor the broader interpretation. They show that neutron stars with extreme magnetic fields are real, active, and capable of producing sudden high-energy events. The difficulty is that local examples are usually seen long after their formation. They reveal the behavior of magnetars, but not always the exact moment that made them. Within the Milky Way, some magnetars lie close to supernova remnants or young star-forming regions, which supports the idea that many come from massive star collapse. Their positions make sense if they are young neutron stars born from the deaths of heavy stars, but the associations are not always simple. Supernova remnants expand and fade. Neutron stars can receive kicks at birth, sending them away from the centers of the explosions that created them. Dense regions of the galaxy can overlap along the line of sight, making distances and associations uncertain. Even when a magnetar sits near a likely remnant, the details of the original collapse remain hidden. The explosion happened in the past, and the early seconds when the magnetic field was built are no longer observable. What remains is a young neutron star with unusual activity and a surrounding environment that may or may not preserve a clear record. These nearby objects are therefore essential but incomplete. They define what Magnetar activity looks like in detail, while leaving open the larger question of which birth conditions produced it. One of the most important behaviors is bursting. Magnetars can release short flashes of high-energy radiation when their magnetic fields rearrange or when magnetic stress affects the crust. Most bursts are modest by cosmic standards, though still powerful compared with ordinary stellar activity. Rare giant flares are far more energetic. They begin with a sharp spike of gamma rays and X-rays, followed by a fading tail shaped by the rotation of the neutron star. Such flares show how quickly magnetic energy can be released once the field becomes unstable. They also show why magnetars can be detected across large distances if the flare is strong enough. A giant flare in a nearby galaxy might be mistaken for a short gamma-ray burst if the distance and host environment are not understood. This creates an observational link between local magnetar physics and extragalactic transients. Some brief high-energy flashes may not require a neutron star merger at all. They may be flares from old or young magnetars in other galaxies. The challenge is to distinguish a compact merger from a magnetic eruption when only a faint, distant signal is available. Magnetars are also connected to fast radio bursts, one of the most active questions in modern transient astronomy. Fast radio bursts are very brief pulses of radio waves, usually lasting only milliseconds, and many come from galaxies far outside the Milky Way. Their brightness implies a compact and energetic source. For years, their origin was uncertain because most were detected only as isolated radio flashes with little information about what produced them. The Magnetar connection became stronger when a known galactic magnetar produced a bright radio burst accompanied by high-energy activity. That event didn't prove that all fast radio bursts come from magnetars, but it showed that a magnetar can produce a radio pulse in the same broad category. This changed the problem. Magnetars were no longer only a possible explanation. They became a demonstrated source for at least some fast radio burst-like activity. The remaining question is how far that explanation extends. Some fast radio bursts repeat, producing many pulses over time from the same location. Others have only been seen once. Some occur in young star-forming regions where massive star magnetars would be plausible. Others appear in environments that may point to older populations or different formation channels. If magnetars produce many fast radio bursts, then there may be more than one kind of magnetar pathway feeding the population. A young magnetar from a massive star collapse could power bursts soon after birth. A magnetar formed in a merger might produce activity in a different environment, perhaps for a shorter time. An older neutron star reactivated by accretion, crustal stress, or binary interaction could add still another route. The radio burst itself is too brief to contain the whole history. Its location, repetition, energy distribution, and surrounding environment have to be studied together. This makes fast radio bursts useful, not only as signals from magnetars, but as possible probes of how magnetars form in different settings. They widen the search from objects that are visibly bright in X-rays to objects that may announce themselves only through sudden radio pulses. Another possible sign of magnetars appears in unusually luminous stellar explosions. Some supernovae are much brighter than normal core collapse events and remain bright for longer than expected. One explanation is that a newborn magnetar forms at the center and transfers rotational energy into the expanding debris. In this model, the magnetar must be born spinning very rapidly, with a strong magnetic field that drains spin energy into the ejector. The added energy heats the debris and increases the light output. This does not mean every superluminous supernova is magnetar-powered. Other explanations can include interaction between the ejector and dense surrounding material, or different kinds of explosion physics. But the magnetar model is important because it connects an observable light curve to the hidden remnant. The brightness and fading rate can be used to estimate how much energy might have been injected, how quickly the central engine slowed, and what magnetic field strength would be needed. These estimates are model-dependent, but they allow distant explosions to become indirect tests of newborn magnetars. If the model is correct for some events, then magnetars can reveal their birth not by appearing as point sources, but by changing the entire brightness history of an expanding supernova. This idea overlaps with the merger problem, but the setting is different. In a massive star explosion, the magnetar is born from a collapsing core and may remain embedded in stellar debris. In a neutron-star merger, the remnant is assembled from compact objects and surrounded by kilonova ejecta. In both cases, the central object may be hidden, and the evidence may come from energy transferred into matter around it. But the timescales, composition, and surrounding environments differ. Supernova ejecta is usually much more massive. Kilonova ejecta is less massive but rich in heavy elements. A magnetar inside a supernova may influence optical light for weeks or months. A merger-born remnant may affect early gamma rays, kilonova brightness, and late radio emission. Comparing these settings helps separate what is general about magnetars from what depends on the birth channel. The general feature is magnetic and rotational energy stored in a compact remnant. The channel-specific feature is how that energy escapes, what material absorbs it, and how long the remnant survives. This wider view makes magnetars less like a single class, with one observable face, and more like a physical engine that can appear through several forms of evidence. A galactic magnetar can burst in X-rays. A distant magnetar may flare so strongly that it resembles a short gamma-ray burst. A young magnetar may help power a superluminous supernova. A magnetar may contribute to fast radio bursts. A merger-born magnetar may leave its mark as delayed radio emission, or as extended high-energy activity before collapse. These are not all the same phenomenon, and they should not be treated as interchangeable. But they may share a central source, a neutron star whose magnetic field is strong enough to dominate its energy release. The main task is to decide when that shared source is truly required and when another explanation is better. Magnetars across the sky therefore create a connected but careful picture. They show that extreme magnetic neutron stars exist nearby. They suggest that magnetic energy can power bursts, flares, radio pulses, and bright transients. They offer possible links between stellar death, compact mergers, and fast radio signals from distant galaxies. At the same time, every link carries uncertainty. A bright supernova is not automatically a magnetar. A fast radio burst is not automatically a magnetar. A long gamma-ray signal after a merger is not automatically a surviving neutron star. The evidence has to be read through timing, environment, energy, and what other models can explain. The value of magnetars is that they give these different events a common physical possibility without erasing the need for caution. They are rare nearby objects, but their influence may be spread across many categories of transient astronomy. The next step is not only to find more magnetars, but to find more complete records of the events around them so that magnetic activity can be tied more securely to birth, lifetime, and collapse. The next stage in magnetar science depends less on one perfect telescope than on the steady accumulation of many imperfect records. A magnetar birth can be too brief, too distant, or too hidden to appear as a single unmistakable event. A merger remnant may collapse before it can be seen directly. A young magnetar inside supernova debris may reveal itself only through the shape of the light curve. A galactic magnetar may sit quietly for years before producing an outburst. A fast radio burst may last only a small fraction of a second and leave no immediate counterpart. These behaviors do not fit well with an observing style that waits for one known object to perform on schedule. They require surveys repeated, systematic observations of large parts of the sky, built not around a single target but around the expectation that the sky is changing whether anyone is looking at a particular source or not. A survey turns the night sky into a time record. It does not only ask what is present, it asks what appeared, what faded, what moved, what changed colour, what brightened in radio waves years after an explosion, and what returned after seeming quiet. For magnetars, this change in observing style is essential because their evidence is distributed across time. The first sign may be a gamma-ray burst. The supporting clue may be an infrared kilonova. The decisive constraint may come from radio silence years later. No single moment contains the whole object. Wide-field optical surveys are important because they can catch the visible and near-visible changes that follow explosions and mergers. When a transient source appears, its brightness and colour can be measured repeatedly as it rises and fades. A supernova, a kilonova, a tidal disruption event, and an unusual fast blue optical transient can all begin as points of changing light, but their later behaviour separates them. Some fade slowly, some redden quickly, some are too bright for ordinary models. Some occur in galaxy regions that point toward young, massive stars, while others appear far from active star formation, where compact mergers become more plausible. A survey that returns to the same regions again and again can build these light curves automatically, giving astronomers a way to identify events that do not match familiar patterns. This matters for magnetars because the central engine is often inferred from how the debris behaves. If a supernova remains bright longer than expected, a newborn magnetar may be one possible engine. If a merger candidate shows red kilonova-like emission but unusual high-energy behaviour, a temporary magnetar may become part of the interpretation. The optical survey does not see the magnetar directly. It reveals the changing material that may have been heated or accelerated by one. Radio surveys add a different layer because they are sensitive to energetic particles and shocks long after the early light fades. The radio sky changes more slowly in many cases, but that slowness is exactly what makes it useful for kilonova debris and magnetar-boosted outflows. A source that is invisible or faint in the first weeks may rise over years as ejecta sweeps through surrounding gas. Targeted radio follow-up can test known merger candidates, but broad radio surveys can find events that were missed at high energies or not recognized at first. This is especially important because jets are directional. A gamma-ray burst may be seen only when its beam is aimed close to Earth. The wider ejecta from a merger, including any magnetar-energized material, can be less narrowly directed. Radio surveys can therefore help reveal a hidden population of explosions whose first beam did not point toward the observer. They can also provide earlier images of the same sky position, making it possible to determine whether a late radio source is new, fading, or unrelated background emission. In a field where non-detections carry weight, repeated radio maps are as valuable as discoveries because they define what was absent before and after the event. Gravitational wave observatories supply another kind of record. They do not observe light at all. They detect the stretching and squeezing of space-time from compact objects moving under extreme gravity. When two neutron stars merge, gravitational waves can confirm the nature of the event in a way electromagnetic evidence alone may not. They can constrain the masses of the objects involved, which then affects the expected fate of the remnant. If the combined mass is high, prompt or delayed collapse into a black hole becomes more likely. If it is lower, a longer-lived neutron star becomes more plausible. When gravitational wave data are combined with gamma rays, kilonova light, and radio observations, the remnant can be studied from several directions at once. The mass informs the lifetime question. The kilonova informs the ejector composition and heating. The radio emission or non-detection informs the kinetic energy carried outward. A magnetar born in a merger may be too hidden to see, but the combined record can still ask whether such a remnant had time to exist. This is one reason the future of the subject lies in coordination. The most complete events will not belong to one wavelength or one instrument. They will be built from alerts passed quickly across the astronomical community and from archives searched long after the first signal. Gamma-ray satellites provide the first notice for some of the most energetic bursts. Optical telescopes search for fading counterparts. Infrared observations help identify red kilonova emission. Radio arrays return later to measure shocks and delayed afterglows. Gravitational wave detectors add direct evidence for compact mergers when the signal is within reach. Each instrument sees a different consequence of the same physical event. The magnetar, if present, is inferred from the agreement or disagreement between those consequences. A long high-energy signal may suggest an engine that lasted longer than usual. A bright optical transient may suggest extra heating. A missing late radio source may limit how much energy was given to the ejector. The strength of the conclusion depends on the whole pattern, not on a single impressive measurement. Large surveys also change the scale of the question. Instead of asking only whether one unusual event produced a magnetar, astronomers can ask how often similar events occur. How many long gamma-ray bursts lack the supernova expected from massive star collapse? How many show kilonova-like colors? How many merger candidates produce late radio emission? How many do not? How many fast radio bursts occur in environments where young magnetars are likely, and how many appear in older stellar populations? A single event may always have alternative explanations, but populations can reveal tendencies. If stable magnetar remnants after mergers are common, repeated surveys should eventually uncover their energetic signatures. If most searches yield only limits, then stable remnants may be rare, and temporary remnants or prompt black holes may dominate. Population evidence is slower than discovery, but it is often more decisive. It turns strange cases into rates, and rates into constraints on the physics of dense matter and stellar death. The coming survey era also brings difficulty. More data does not automatically mean clearer answers. Large surveys produce enormous numbers of alerts, many of them ordinary variable stars, active galactic nuclei, asteroids, supernovae, or instrumental artifacts. The rare events are buried among common ones. Classification must be fast enough to guide, follow up, and careful enough to avoid false certainty. Machine learning can help sort candidates, but the physical interpretation still requires models and judgment. A source that looks unusual may be a new kind of engine, or it may be a known kind of event seen from an unfamiliar angle. A missing signal may be meaningful, or it may reflect sensitivity limits. Surveys widen the net, but they also demand discipline. The goal is not to label every strange transient as a magnetar. The goal is to recognize when magnetar physics is truly needed and when the evidence can be explained without it. In that careful sense, surveys are not only discovery machines, they are memory systems for the sky. They preserve what happened before a burst, what changed during it, and what remained afterward. They allow astronomers to return to old positions with new questions. They make it possible to see whether a radio source was already present, whether an optical transient had a precursor, whether a galaxy hosted similar events before, and whether a supposed absence is deep enough to matter for magnetars whose lives can be brief, irregular, and hidden. This memory is vital. A birth may be missed, but its after-effects may still be found. A remnant may collapse, but its energy may still move through debris. A burst may last milliseconds, but its location may point to an environment that reveals its origin. The short, violent life of a magnetar therefore becomes more readable when the universe is observed not as a set of isolated targets, but as a changing system. The sky becomes a record, and within that record, magnetars leave traces that are rarely simple but increasingly possible to connect. The short, violent life of a magnetar is not measured only by how much energy it contains, but by how quickly that energy can shape its surroundings before time and gravity reduce its influence. In a massive star collapse, the remnant may be stable as a neutron star, and its magnetar phase can unfold across thousands of years as the magnetic field stresses the crust, heats the surface, and powers bursts from a cooling compact object. In a neutron star merger, the same kind of magnetic intensity may exist under more urgent conditions. The remnant can be too massive from the beginning, supported for a limited time by rotation and heat, already losing the support that allows it to avoid becoming a black hole. These two settings make magnetars difficult to describe with a single lifetime. Some may survive as neutron stars long after their strongest activity fades. Others may live as magnetars for only a brief interval inside expanding debris. What connects them is not a shared duration, but a shared physical state, a compact star whose magnetic field becomes the main engine of observable energy release. The violence is concentrated into the field, into the crust and magnetosphere, into winds and bursts, and in the merger case into the final contest between rotation and collapse. That is why the life is short in a scientific sense, even when the object remains for much longer. The active magnetar phase is a temporary condition, not a permanent guarantee. The known path from massive star collapse begins with a core that has passed beyond ordinary support. A neutron star forms when matter is compressed into a state dominated by neutrons, and a magnetar forms when the magnetic field reaches a level strong enough to control much of the remnant's behavior. The likely ingredients are clear, even if their exact combination is not. The newborn neutron star must carry or create an extreme magnetic field. Rapid rotation may help. Internal motion may amplify the field through a dynamo before the crust settles. The explosion around it may hide the remnant for a time, while later X-ray and gamma-ray activity reveal that the field is still releasing energy. This picture explains many galactic magnetars and connects them naturally to the deaths of massive stars. It also explains why the objects are uncommon. A neutron star can form without becoming a magnetar. A collapsing star can lose too much rotation before death. The remnant can fail to build the necessary field, or it can become a black hole instead. The result is a narrow outcome within an already extreme process. Magnetars are not ordinary neutron stars with a slightly stronger field. They are remnants in which magnetism has become the controlling feature of the early life. The merger path adds a shorter and less settled version of the same idea. Two neutron stars can spiral together after a long loss of orbital energy, collide, and form a single remnant surrounded by neutron-rich ejecta. In that collision, magnetic fields can be amplified by turbulence and shear, while rapid rotation supplies a large reservoir of energy. If the remnant survives, even briefly, it may behave like a magnetar hidden inside a kilonova. It can inject energy into the debris, extend high-energy emission, and perhaps accelerate ejecta enough to produce a late radio signal years afterward. But survival is the uncertain part. The combined mass of the two neutron stars may exceed the stable limit. Rotation can delay collapse, but as the remnant spins down, support declines. The magnetar can therefore be both powerful and temporary. Its field may influence the environment while its mass prepares its end. In this version, a magnetar is not only a remnant of stellar death, it is a transitional object between merger and black hole, leaving evidence through energy transfer rather than through long-term existence. GRB 211211A remains valuable because it sits close to this boundary. Its gamma-ray duration was long, but its optical and infrared behavior did not fit the usual massive star collapse picture. The absence of a normal associated supernova and the presence of kilonova like red emission supported the idea of a compact merger. That combination made a central magnetar-like remnant plausible, because a merger that leaves a neutron star for longer than usual could keep powering emission after the first burst. Yet the later radio observations did not reveal the bright signal expected if a stable, long-lived magnetar had strongly boosted the ejecta. The result does not erase the magnetar possibility. It shortens it. It suggests that if such a remnant formed, it did not live as a stable engine able to deliver the largest expected energy into the surrounding material. It may have collapsed after a brief phase. It may have added some energy without leaving the full late radio signature. It may have been a temporary magnetized neutron star whose strongest evidence is found in the limits placed on what it failed to do. That conclusion is cautious, but meaningful. It turns a distant event into a test of remnant lifetime. The broader population points in the same careful direction. Known magnetars in the Milky Way show that magnetic neutron stars can burst, flare, and glow in high-energy radiation. Fast radio bursts show that at least some very brief radio signals can be produced by magnetar activity, although not necessarily all of them. Superluminous supernovae may in some cases be powered by newborn magnetars that transfer spin energy into stellar ejecta. Kilonovae and unusual gamma-ray bursts may reveal still another channel, where magnetars are made by mergers and sometimes collapse before they can be directly observed. These links do not reduce all strange transients to one explanation. They show that magnetars can act as engines in several environments, and that each environment leaves a different kind of evidence. Each method is incomplete by itself, but together they build a picture of magnetars as brief, energetic phases in the lives of compact remnants. The most important remaining uncertainties are physical rather than merely observational. Dense matter is still not fully understood at neutron star core pressures. The maximum mass of a neutron star is still being narrowed. The details of magnetic field amplification in the first moments after collapse or merger are still difficult to simulate completely. The way magnetic energy travels from the interior to the crust, from the crust to the magnetosphere, and from the magnetosphere into radiation is still an active field of study. These uncertainties matter because small differences can change the outcome. A little more mass can turn a neutron star into a black hole. A little less rotation can prevent a strong dynamo. A different surrounding density can hide a radio signal that would otherwise have been detected. A different viewing angle can make a jet bright or nearly invisible. Magnetars live at the intersection of these narrow conditions. Their behavior is not random, but it is sensitive to birth, environment, and internal physics. This is why surveys and long-term monitoring are so important. The next decisive evidence may not come from one dramatic observation, but from many records compared over time. A gravitational wave event with a well-measured mass, a kilonova with clear color evolution, a gamma-ray signal with extended activity, and a late radio detection or strong non-detection would all constrain the same remnant from different directions. Repeated discoveries will begin to show how often mergers produce prompt black holes, temporary neutron stars, or stable remnants. Radio surveys may find delayed afterglows from events whose first jets were not aimed toward Earth. Optical surveys may identify unusual explosions whose light curves require central engines. High-energy satellites may catch magnetar flares close enough to separate them from merger bursts. Fast radio burst localizations may show whether magnetar activity prefers young stellar regions, older populations, or both. The subject advances by connecting these pieces without forcing them into one answer too early. Magnetars are likely not a single story, but a set of related outcomes produced when neutron star matter and extreme magnetic fields meet the right conditions. What remains after all these paths are considered is a restrained but powerful portrait. A magnetar can be born when a massive star collapses and leaves behind a neutron star with a field strong enough to dominate its energy release. It can also, perhaps, be born when two neutron stars merge and briefly create a remnant whose rotation and magnetic field reshape the surrounding debris before collapse. Its active life may be long enough to produce repeated bursts over thousands of years, or short enough to exist only as a hidden engine during the fading of a kilonova. In either case, the object is defined by stored magnetic energy under extreme conditions and by the limited time over which that energy can be released in observable form. A magnetar is therefore not only an exotic object at the edge of stellar death, it is a test of how matter behaves when compressed, how magnetic fields are amplified, how explosions are powered, and how compact remnants survive or fail. Its life is violent because the energy density is enormous. It is short because the field evolves, the star cools, and in some cases gravity ends the neutron star itself. What remains is the trace of that process: a flare, a pulse, a brightened explosion, a delayed radio signal, or an absence that limits how long the remnant could have lived. The story of a Magnetar settles into a quieter form once its brightest moments have passed. A massive star collapses, or two neutron stars merge, and for a limited time the result is a compact object ruled by magnetic energy. Around it, matter responds in different ways. A crust shifts under stress. A magnetosphere fills with currents. Debris expands, cools, and carries outward whatever energy the hidden remnant was able to give. Some traces are immediate, appearing as bursts or high-energy emission. Others take years to emerge, as ejector reaches surrounding gas and turns motion into radio light. Some traces never appear at all, and even that absence can become part of the evidence. This is the careful shape of the mystery. A magnetar is not only a rare neutron star with an extreme field, it is a brief physical condition in which gravity, rotation, dense matter, and magnetism meet at their limits. Sometimes the neutron star remains, fading slowly as its field evolves. Sometimes the remnant may collapse before it can be directly known, leaving only constraints in the debris around it. The strongest questions remain open, but they are no longer vague. They concern the mass a neutron star can hold, the speed at which magnetic fields grow, the lifetime of merger remnants, and the ways hidden engines reveal themselves through changing light. Each new survey, each late radio observation, each gravitational wave detection, and each unusual burst adds another small boundary to the picture. The violence becomes understandable not as chaos, but as physics under rare conditions, and when the signals fade, what remains is a patient record of energy released, energy withheld, and matter pushed close to the edge of what a star can become.